So far, we've seen the reposition strategy. We've also seen that the reposition strategy is actually an optimal deterministic strategy. However, it's a little counterintuitive for why it would be the best one, especially in practice where if you imagine, okay, I want to get from S to T, going back to the source every time and recomputing a shortest path, sure, you can do it, but it sounds like, oh, well, it's like you're wasting a lot of space going back and forth like that. So I want to present you another strategy that we're going to explore. So this strategy, I'm going to refer to it as the myopic strategy. In literature, it's sometimes called the greedy strategy. So remember, we're going to presume that we're computing a shortest ST path. If we travel along the ST path and we hit a trap edge, we don't cross over the trap, right? We stop. We need something to do in that result. Like, what are we going to do? So this is what I'm laying out. So if ever the traveler has to stop at a vertex U as it reveals a trap edge E. That G is looking a little sad there. Trap edge E. So it can't continue any further because you can't cross over the trap. This is what we're going to do. So instead of going to S, we're just going to continue down this way. We're going to travel next. So next we're going to travel the shortest UT path. So we're going to go from U to T. We're going to find the shortest UT path without E and edges discovered to have traps. See, this one sounds a little bit more natural to try, right? So like this sounds like something that you might try to do. Can I at least get some partial agreement on that one? Is that, sure, you may have thought of the other strategy, but this one sounds like something that the first thing you would try, because remember, you have the map. You know where everything is. You just don't know. The only thing, okay, I shouldn't say everything. You just don't know that there's more trap edges unless you've encountered all K of them at most. So this one seems a little bit more like something a human would do, right? This sounds like something that the first thing you might try to do. So again, the pseudocode for this I'm going to include in the notes, just for the sake of time. But I'm going to do an example with you to show you how you would carry this out. So let's do an example. So I'm going to use the same haunted house layout that we had before. So I've got my stairs, the fast track, my maze of doom. And of course, I got stairs here to go back over here. This is the teleporter room. So the teleporter room had that edge with weight 1 or length 1. 1, 6, 7, 1, 1. And I guess got to label the vertices. S, T, 1, 2, 3, and 4. There. I think I got all the edges. I think I got them all. There we go. So we're going to carry out our myopic strategy. So remember, as earlier, we computed the shortest ST path before. We showed how to do it with Dijkstra. So here we go. So remember, Dijkstra's algorithm would tell you to do this. Take the traveler from S. You're going to go like this. That would be the shortest ST path, as we established earlier. So I haven't shown you where the trap edges are. I'm going to use the same example I used last time. So I'm doing this for the sake of making it easier for you to see what's going on. But remember, as far as the algorithm is concerned, it doesn't know where these are until it encounters them. So remember, the spooky hall had a trap at it. We made the teleporter itself have a trap on it. And we got the fast track also has a trap on it. So you're going to see very quickly that we're going to not be able to use our shortest ST path to reach T, right? It can't cross this trap edge. In fact, when it begins, when the traveler starts walking and leaving S, it will discover this trap edge. And then it will proceed to go this way, right? That's where the traveler will go, right? But it'll stop right here because there's a trap edge that reveals that trap edge. So unlike the reposition strategy, the myopic strategy now says that you're supposed to travel to the next shortest UT path. So now we compute the UT path. Remember, this is U right now. That's U right now. Not you, but that's you. Vertex 1 is U. Not literally, okay. So anyways, we're going to compute now the shortest UT path. Well, it doesn't take a genius to notice that it's really just taking a beeline right through the maze of doom, right? The edge 1T. So what would happen instead is it would compute the shortest UT path, which tells you to go that way, and the traveler will follow along with that. And it happens to be, in our case, that we go from U to T, which gets us to T. There's something I haven't said, though. Does anybody notice something that I omitted to you about finding a shortest UT path? Remember, this one has length 8. So remember, this process will compute the shortest UT path. There is actually another shortest UT path, just it uses a trap edge. So notice I can go back to S, I can go through from S to 2, and then I go through the teleporter from 2 to T. That has length 8, right? Notice that if you took that route instead, you would get stopped right here, and you would have to recompute now a shortest 2T path. But you've revealed this one. I must stress that when we reach T, we reveal this trap when we finished. But it doesn't really matter. But the point is that if we try going back this way, we'll end up taking a big penalty by having to then go all the way back. Do you see that? So if we pick that shortest ST path instead, it would actually be quite a big penalty for us. Maybe not, so it's more like the reposition strategy in that regard. Do you see that? In fact, it can get really bad. So anyways, that's an example. Are there any questions about the example here? So you notice here that this reminds you of the path that we got last time. Except we didn't have any of that back and forth business. This should come to you and say, hey, look, that's actually pretty good. We didn't have to retread back to S. That's great if you noticed here that the second shortest path, once I hit a trap edge, was actually really close to where I was. This is actually a really natural intuition. So the work that this myopic strategy, a lot of this work was, it can be found in a paper by these authors. In 2009. So these researchers actually showed that if your graph exhibits a property that they observe with what they call urban traffic, the authors of that called it, I believe, the they call it the pseudo, I believe it's the pseudo grid condition, which a lot of urban traffic environments actually exhibit the pseudo grid condition. And in the paper that by these authors, they show actually there's a couple of cases for which you can get the competitive ratio if you were to actually sit down and actually prove it with the myopic strategy. In those cases that satisfy the pseudo grid condition, you can actually show that the competitive ratio is actually quite small, which means it matches your intuition, because when you go to a city where there's a grid where you can travel, say if there's a blockage at one intersection, what do? You just simply go around it, right? So this is something that they observe. So I must stress that this strategy in itself is intuitive, but also can lead to really bad results. And I'm going to show you that. So this pseudo-grid condition, they discussed that in the paper I've mentioned in my references. If you want the paper specifically, just bug me at the end of the talk, okay? So this is good in practice for urban environments where they exhibit the property I just described, where the second shortest path is very close to the length of the shortest path. That makes sense? And that's very intuitive. If you have an urban environment that's very dense with many intersections where the blockages are going to be not as heavy in this case. And I must stress that there's a little bit more to this condition, but that's the main idea behind it. But anyways, I got to show you what happens with this myopic strategy. Because remember, in this example here, I happen to just pick the shortest UT path. However, I could have been rerouted all the way through a good chunk of this graph and then gone all the way back, right? Well, I'm going to show you that it's even worse than this. So let me show you what I'm talking about. And it's going to be one of the funniest things I'm going to draw on the board today. So I'm going to feel like John Madden here. So just prepare yourself. Prepare yourself. So I'm going to have S. I'm going to have T. I'm going to have a vertex right here. So prepare yourself. If you're drawing this, leave yourself some space, okay? This is going to be a little bit of a gong show here. I'm going to introduce another edge here. So this is going to be an instance that I'm going to construct for any epsilon that is greater than 0. So just presume that there's an epsilon greater than 0. So the intuition will be that epsilon is very small. But it doesn't have to be. So we're going to have an edge that goes from S to T directly, called with a weight 1 plus epsilon. This edge is going to have weight 1 minus epsilon over 2, and this edge weight is going to be epsilon over 2. Okay, before we get into the full-blown instance, I'm going to talk about this. So let's see here. We've got, if I were to ask you what the shortest ST path is, which one is it? Is it from S to T directly, or is it through that vertex over there? It's this one, right? That one right there. We wouldn't take this one, the one that loops around like that. We would like to take this one because its total length is 1. Do you see that? So its total length is 1. So that's the shortest one. But what I'm going to do is I'm going to put a trap on this edge right here. Now can you see that if I put that trap edge in there, this would actually be the better route. So if I knew where all the trap edges were, I could just take this B line, I go right from S to T, boom, there you go. Now, I'm not happy with this because if you notice, if I were to use the myopic strategy, it would tell me to go here, right? Because this is the shortest ST path at that time. Then it computes the shortest ST path. And so what it means is that I can't cross this, so it comes back this way and then zooms around like that, making the myopic strategy have a longer way around. Do you see that? Now, I don't want to actually have that happen, though. So what I'm going to do instead is as follows. What I'm going to do is I'm going to create a path that's going to make the myopic strategy, go further and further away from the source, which happens to have the edge that is the optimal ST path. I'm going to try to drag the traveler further and further away from S and get a path that goes to T. But I'm going to need to make sure that I always find a way to get the myopic strategy to reroute the traveler away from S. So I'm going to try to push it away from S. But I want to make sure it never uses this red path. Is everybody clear? Is that clear, everybody? We're not going to use the red path. I don't want to use the red path. I want to instead make the traveler go on a weird little chase. So what I'm going to do is I'm going to now introduce another vertex. It's going to be, its weight is going to be epsilon over 4 away from T. And I'm also going to introduce another one, epsilon over 8. And I'm going to have more of these. In fact, there's going to be, because I'm going to have K traps, right? I'm going to have K of these. Each one of these is going to be, just to be clear, this would be, each one of these will be epsilon over 2 to the power of I for some power of 2, starting at 1. Because I have epsilon over 2, epsilon over 4, epsilon over 8. I'm going to have it where it goes by powers of 2 like this. And then what I'm going to do is watch this. Watch this. This is where I'm going to feel a little bit like I'm going to go boom. So I'm going to make an edge like this. The weight of this edge is going to be 2 minus epsilon over 4. So notice that it's a very similar structure as this one did. It would never go back to S and go through the red path. Instead, it would take and go this route. But here's the thing. This is how I'm going to trap the traveler with this myopic strategy. So watch this. I'm going to put a trap right here, and I'm going to repeat this process. So I'm going to make this weight be 4 minus epsilon over 8. So notice that 4 minus epsilon over 8 plus epsilon over 8, that's just 4. And you could show that the alternative route will always take the form of like some power of 2 plus epsilon over that power of 2. So it always ends up being that you would always want to go this way, not go back to S and through the red path. So we're going to put a trap edge here. And you're going to repeat this process. I feel like I'm drawing a turkey. You know those children's art books where you have like the turkey and you like put it down and you're tracing it out and then you make it into a turkey? That's what I feel like I'm drawing right at the moment. So I got 8 minus epsilon over 16. And you'd keep doing this until you eventually get the following edge weight. Keep in mind there's more trap edges in between here. There'll be K of these. The last one will be 2 to the power of K minus epsilon over 2 to the power of K plus 1, which you should expect because everyone is the power of 2 minus epsilon over the next power of 2. And here's the catch. Based on what I described to you, which I'll have more details in the notes, and notice that there is no trap edge right here, just to be very clear. This is the last one. Notice that notice it's epsilon 2, 4, 8. Is this going up 1, 2, 3, 4, 5, 6, all the way up to K plus 1. So there's K plus 1 possibilities here. What the myopic strategy would do here, for this instance, is it would go like this, 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 and it'll keep doing this all the way around. And let's figure out what's going on. So what's the length of this path then? So notice that I have something that looks like it's growing geometrically. So let's put the sum together. So the length is at most the sum from I is equal to 0 to K of each one of those edge weights that I go through. 2 to the power of I minus epsilon over 2 to the power of I plus 1. Well, you notice that all of these are just subtracting off a chunk. So I'm just going to get rid of it. So this is at most, so I'm going to bound it from above. So now I just have the sum from I is equal to 0 to K of 2 to the power of I. You would recognize this as a geometric series. So what you do now is you're just going to now take this And there's a nice known closed form for this. It's going to be exactly equal to 2 to the power of k minus 1. And remember, the optimal solution, if you knew where all of the edge weights, well, sorry, all the trap edges were, that's 1 plus epsilon. If you take epsilon, approach it to 0, the competitive ratio, like what would the competitiveness in this instance, would be exactly 2 to the power of k minus 1. Or at least it's actually, sorry, it isn't exactly that. It is going to approach that. I should be a bit more precise about that. And in fact, you can show that even me shaving off that little bit everywhere doesn't make any difference. It's just that it's just going to be that if you make epsilon really small, those little bits are going to just stay really tiny, okay? So I'm going to give you one last strategy. So here's strategy number 3 for the K Canadian Traveler problem. So this is what we're going to call the comparison strategy. So you're going to see that this is actually going to be a combination of the reposition strategy with the myopic strategy. So you're going to find that this is going to address the faults, at least at least the intuition should be clear that we need to get it so that you can't get too far away from an optimal ST path by making locally optimal choices that send you in the wrong direction. So we need some way of kind of like dragging it back so it doesn't go drifting off like that, okay? So we don't want our traveler to get too lost in the haunted house. But I must stress, each time when it does this, it does get shorter and shorter, but it might take and do a lot of paths to get those shorter and shorter paths every time we get trapped by, well, we run into a trap edge. Okay. So suppose the traveler encounters a vertex U and cannot travel further as E, we'll say as it encounters. So as it travels, it cannot travel further as, sorry, cannot travel further, I'm thinking about a fun way to put this, further along edge E as it has a trap we're going to let E prime be the edges E and all discovered trap edges. So keep in mind there could be more. So from vertex U, you're going to do the following. There's 2 possibilities. Here's the first possibility. If the length of shortest UT path, if the length of a shortest UT path without using edges E prime is at most the length of the shortest ST path without using edges E prime. So do you see how I'm comparing the shortest UT path from that current point versus the shortest ST path? So if I go from U to T and it's that length of that path would be, now keep in mind, I don't know if I can actually travel over it to T. there might be more traps. If this length of this path that I compute is no longer than the shortest ST path without using the trap edges I have so far, then it's suggested to use the myopic strategy. Then use the myopic strategy. So if you see that your shortest UT path is not going to be longer than the shortest ST path, in the case of when we don't use the trap edges that we know so far, use the myopic one. Otherwise, we're going to reposition. Otherwise, use the reposition strategy. So I'm going to state this as a theorem for you. So I'd prove it with you, but I think the proof is actually pretty accessible in itself, like in the actual paper. And you're going to tell right away, since you're given two choices like this, you're going to see that this is going to be very much about a trade-off that happens between these two choices, these two different policies. And you're going to see that this is sort of like the sweet middle when you allow this to happen. So an algorithm that uses the comparison strategy, as we've discussed previously with the other strategies, the comparison algorithm is 2k plus 1 competitive. 2k plus 1 competitive. Remember, k is the number of traps. Competitive for the K Canadian traveler problem. So so remember, reposition strategy matches this competitive ratio on its own. But as we've established previously, it requires you to go back to S a lot and recompute an entire shortest ST path for your traveler, by the way. And keep in mind, you might hit a lot of traps in that process. So this strategy is suggesting to you that you can actually not have to do that. You can actually use this myopic strategy to try to get yourself incrementally closer to T in certain circumstances, and you still end up with this competitive ratio of 2k plus 1. So this also matches the optimal deterministic lower bound on for the K Canadian traveler problem.